Okay, folks, we are in chapter 6. This is the normal distribution. We are in section 6-2. This is the applications of the normal distribution, and this is video recording number 4. Okay, so as I mentioned before, I'm using the PDF version of the text. So this is edition number 9. It's slightly different, not significantly different from edition 10. So we're almost at the end of section 6-2, and what the author's talking about here is determining normality. Now the idea is that the normal distribution is very handy for us because it's easy to do the calculations, and it would be wonderful if everything was had this normal distribution. However, obviously in real life, not everything is normal. Not everything has a normal distribution. It can have all kinds of bizarre shapes. So when you get a bunch of data, one of the things that you would want to do is try to decide what kind of a distribution should be used to model this data. And certainly you would hope that it would be normal. A lot of things are normal, but you just don't know until you do the tests. So what I want you to get out of this part of the section is merely that there exists these tests. I'm not going to assign it as part of the chapter quiz. So those problems, I think it's 33 and 34 in the textbook of the chapter quiz. 33 and 34 deal with determining normality. It's an awful lot of busy work, and in real life it's all done on a software program anyway. But I want you to be aware that these kinds of things exist. So if you're a data scientist of some sort, one of the first things you would do is try to decide what kind of a distribution would be used to model the data. Well, certainly this would be one of the tests that you would run. Okay, so as he says here, this normal shape or this bell-shaped distribution is only one of many types of tests. It can be all kinds of things. It's very important. It's very important. However, we want to know. So one of the things we do is draw a histogram. We draw a histogram and we check its shape. If it's not bell-shaped, well, then it can't possibly be normally distributed. That doesn't sound very scientific, but it's so easy to draw those using the computer software, then that would probably be the very first thing you would do. The next thing you might do is check for skewness. If it's too skewed, then you don't want to use it. So we have to, that's called the Pearson coefficient. Pearson coefficient of skewness is used. It's also called the Pearson's index of skewness. So if you Google it, you might see both names. Okay, so the very first thing you need to know is, how do you calculate what is this coefficient? The coefficient normally just means a number. So the Pearson's coefficient, it's now X bar and S. Remember, because it's X bar, that's telling us that it's dealing with a sample, not a population. X bar is the mean of the sample. S is the standard deviation of the sample. And then median, we know what that is. That's the guy right in the middle. So here's the formula. It's X bar take away median. In other words, how far away from the median is your X bar? If it's a normal distribution, X bar and the median will be the same, or very close to the same, closer and closer to 0. So 3 times 0 is 0, so the Pearson's coefficient would be 0. So as you get further and further away from the median, as the X bar, the sample mean gets further and further away from the middle point, Pearson's coefficient gets bigger and bigger. And then the yardstick that we use to kind of, what kind of units are we using is the standard deviation. Are we talking 1 standard deviation, 2 standard deviations? Are we talking a half of a standard deviation? That's the yardstick that we use. Well, what's the criterion that we use? If the index, if this PC is greater than or equal to a +1 or less than or equal to -1, it can be concluded that the data are significantly skewed. So you probably wouldn't want to use the normal distribution. In addition, you should check it for outliers by using the method shown in chapter 3. Outliers, remember what that means, is just data points that are just way off, just totally weird. Like I think I may have used the example before we had to switch over to online. If Bill Gates walks into the room, he's an outlier with respect to a couple of things. He's an outlier with respect to his income. He might be an outlier with respect to his age. So, he's different from the rest of the students. That's called an outlier. Okay, so there's a method for that. There's a technique for that, which they explain in chapter 3. So that's something else that a data scientist might do. And here's a couple of examples. You go ahead and look at those, but I'm not going to be testing you on those, and I'm not asking you to do the chapter quiz. I just want you to know that these methods do exist, okay? And here's an example of drawing a histogram, and it looks approximately bell-shaped curved, okay? And for this particular data set, he cranks through it, and he calculates the Pearson coefficient, and as you can see, it's not greater than +1. It's not less than -1. So we say, well, it's not significantly skewed. And you check for outliers. There's a very kind of a complex way of doing that. It looks harder than it is, but there's a way of doing that, and there's no outliers. So you say, hey, listen, the histogram is approximately bell-shaped. The data is not significantly skewed. There's no outliers. What the heck? We can call this approximately normally distributed. Okay? All right, so that's the end of this video, the end of section 6-2.